Okay, number 11. You've got a bridge being held up by some suspension cables. Says there's 240. The bridge is 240 long feet. Has towers at both ends that are 140 feet tall. Cable comes within 40 feet of the ground. Other stuff. There's a dot right here. That is point A. It says, what is the vertex of the parabola? So we can see here's the y-axis. The road is the x-axis. So that makes this right here appears to be the vertex of the parabola. So that point has no x direction, so that's 0, and we were told it's 40 feet off the ground, so it's at 0, 40. Point B says what is the coordinate of point A? So A is half the distance to the right. So if the total distance was 260, we are 130 feet to the right, and we were told that we are 140 feet in the air. And part C says, use the points from A and B, find the function that models the height of the cable above the road as a distance x feet from the center. So since we have the vertex, we can use a vertex form, y equals a times x minus h squared plus k. Because we know that this is h, this is k. So if I start plugging in what I know, because I also know that this is an x and a y value, I can say that 140 is equal to a, we don't know that, times x minus 0 squared plus 40. And, sorry, that shouldn't be an x. We know what x is. X is 130 minus 0 squared plus 140. Oops, plus 40. Sorry about that, k is just 40. And so we can solve this. We can subtract the 40 from both sides. So 100 is equal to a times 130 squared. 130 squared is 16,900, so we can really just divide both sides by 16,900. And I get A is 1 over 169. So my function for that parabola is y equals 1 over 169 times x squared plus 40. All right, moving on to number 12. So this one is very similar to number 9. It's another rectangular piece of material, 25 by 18, cutting out equal squares from the corner and turning them up. So think about the open shoebox again, or the lid to a shoebox. So part A says draw a diagram. So the diagram we're going to draw, here's my piece of material. It has a length of 25 centimeters, a height of 18 centimeters, and then we're going to be cutting a square corner out of each side. It has a length of x centimeters. That's part A. Part B says write the volume of the box as a function of x. So it's, the volume is equal to the length, which this is my length, which is 25 minus the two x's that I cut out for the two sides. It's 25 minus 2x times my width, which is this side, which is going to be 18 minus my 2x's, times my height, which when I fold over all the sides, looks something like that. It's 18 minus 2x, 25 minus 2x. So my height is just x. So there's my function for the volume. C says determine the range, or the domain. So let's think about this first of all. If we're talking about domain of an actual object, the space filled by an object, it can't be negative, so we know our domain has to start at 0, and specifically if it's not greater than 0, then it's not going to work. Like, it can't be 0. If it's 0, it's not an actual shape. So we're going to have a parentheses 0 until, and we got to figure out what the ending value is. So I'm going to go over to the graph, and when we look at the graph, it looks like I've got, I cross once and then I cross again. Well, I cross at 0, then I cross once and I cross again. I'm not worried about this second one, because once it crosses, it goes into the negative values and it no longer matters. So I'm only concerned about what is this point right there. I'm going to go menu, analyze graph, that's a 0, find it on both sides, and that appears to be 9. So my domain is 0 to 9, and we're also not going to include 9, because if it's either 0 or 9, my volume is 0. So I'm not going to include those values. Part D, graph the function. And so we already did that. And we want to find the maximum volume. So once again, we need to look up towards the top of this graph. So I'm going to change my scale. The last one was 550. I'm going to try 600 because I know this is a little bit bigger box and I can't quite see it. So I'm going to go a little bit bigger. Remember, your window is something that makes sense to your graph. I'm going to bring that down just a little bit. So now I can see the top of the graph. So, and if you notice, over here, when I said we didn't care about those other values, so see how it dips underneath? So these are all impossible values, and then it starts counting again, but that goes to infinity. We don't want that. That's why we don't include anything past the 9. But we do want the maximum, so we go menu, analyze graph, max, find my 2, and so find the x value that yields the maximum volume. So my x value is 3.44 centimeters, and that leaves me with a volume of 693 centimeters cubed. So the answer was x equals 3.44. And then E, what are the dimensions of the box? Well, again, plug in 3.44 for my side lengths. So 3.44 centimeters is my height, my length, and my width. I need to find those real quick. I'm going to go to the calculator. So 25 minus 2 times 3.44. That's 18.12 centimeters. And 25 minus, not 25, 18 minus 2 times 3.44 is 11.12 centimeters. So those are the dimensions of my new box. Alright, number 13. We've got a rectangle is bound by the xy axis and the graph of y equals 10 minus x. So this curve is 10 minus x squared. Part A says create a function for the area of the rectangle. So we want an area of this. We know the area is base times height. Well, the base of this rectangle is whatever value x is, right? That's the x-axis, so whatever point this is, that's just x. The height of this rectangle happens to be, so if I move this rectangle to there, or if I move it to here, regardless of where I'm at, the height of the rectangle is the function value. So the height of my rectangle at any point is 10 minus x squared. So we know that in general the area is base times height, but if we plug some stuff in, we get x times 10 minus x squared. So that is the area of my rectangle. Part B says determine the domain of the area function. Well, the domain is going to be similar to the last problem. It's going to go from 0, not including 0, because if it's 0, we just have a line, not a rectangle. And it goes up until whatever this point right here is. So we can figure that out since we're already in factored form. These are my two zeros, the left and the right side. So x equals 0 is one possible one. Got it. And the other one is 10 minus x squared equals 0. So negative x squared is equal to negative 10. X squared is equal to 10. So x is equal to plus or minus radical 10. We don't want the negative value. So my domain goes from 0 until the positive square root of 10. So that's my domain. We can verify that with the calculator if we need to. Part C says find the area when a is 2. When x is 2. So we're just going to plug in what we know. A is equal to 2 times 10 minus 2 squared. So that's going to be 10 minus 4, which is 6. So we got 2 times 6, which is 12. And we aren't given units. So we're going to say units squared. Part D says determine the maximum area. So to determine the maximum area, we're going to go to a graph. And we're going to plot the function x times 10 minus x squared. And don't forget to put the multiplication sign in between, doesn't know what to do. And we get this guy. So it looks like obviously we have a negative area over here on the left. And if I move up a little bit, so there's my maximum right there. Analyze graph, max. And we get 1.83 and 12.2. So my maximum area is 12.2 units squared. And that happened to be at when x was 1.83 units, but that wasn't important. It just said what is the maximum area. Then E, another bad question. What are the dimensions of the rectangle with an area of 12? We already found that. When the area was 12, we had our dimensions. It was 2 times something. So the base is 2 and the height is 6. And that's it for number 13. All right, 2 problems left, and these are the graphs. So if I'm going to graph a rational function, I'm going to start by finding the x and the y-intercept. So my y-intercept is, actually I take that back. It wants me to find the domain first. For the domain, we set the denominator equal to 0. So 2x squared plus 5x minus 3 equals 0. I think that's going to be factorable. I mean, negative 6, positive 5. That's going to be 6, negative 1. Divide everything by 2. So that leaves me with x plus 3, x minus 1/2, which turns that into x plus 3 times 2x minus 1. If I solve each of those, x is equal to negative 3 or 1/2. So those are my restrictions on the domain. So my domain itself is x can't be negative 3 or positive 1/2. Part B, find the vertical asymptotes. Well, the good news is we already found the vertical asymptotes. They're at x equals negative 3 and positive 1/2. We do have to check though, because we might have something that cancels out. So we should factor the top if it's possible. So if we factor the top, we get negative 15 and positive 12. Does anything multiply to 15 and add to 12? That's going to be nope. So it does not factor, which is good. So there's my vertical asymptotes at negative 3 and positive 1/2. I'm going to go ahead and graph those now. So we've got negative 3 asymptote right here, positive 1/2. Part C says, are there horizontal asymptotes? And there are. Remember, we look at our highest power. Those are both squared. So if they're the same, we divide our coefficients. So that's at 5/2. That's my horizontal asymptote. So I can graph that. 5/2 is at 2.5. Make these look a little bit better. Alright, D says slant asymptotes. Well, if there's a horizontal, there can't be a slant asymptote, so there's none. E, end behavior. Got to graph it before we can find the end behavior. So to graph it, we're going to make a table of values. We should probably find the x and the y-intercepts. The y-intercept, remember, you make all the x's 0. So if we make all these x's 0, that's gone, that's gone, that's gone, gone. And I'm left with -3 over -3, which is y equals 1. And the x-intercept is when the numerator is equal to 0, which is 5x squared plus 12x minus 3. So that equals to 0. Use the quadratic formula. -12 plus or minus the square root of 144 minus 4 times 5 times -3 all over 10. Can do some quick math over here. 144 minus 4 times 5 times -3. I'm going to take the square root of that. And then I've got -12. So I end up with x equals -12 plus or minus 2 square root of 51 all over 10, which is -6 plus or minus the square root of 51 over 5. Let's see if we can get an approximate answer for that. -12 plus the square root of 51 over 5. I get almost -1. And -13. Alright, let's go ahead and make a table of values. So we've got some stuff going on in between the two graphs. So let's try like 0. Well, at 0, we know that y is 1, so there's a point here. Let's try -1 and -2, see what happens. Let's try -4. I'm going to get rid of this stuff just because it's in the way. I'm going to try -4 because it's outside the asymptote, and maybe -5, see what happens there, and I'm going to try +2 and +3. So there's my asymptotes. So I'm going to go ahead and plug this in. So we've got 5 times -1 squared 5 times negative 1 squared plus 12 times negative 1 minus 3 over 2 times negative 1 squared plus 5 times negative 1 minus 3. And I get 5/3, which is negative 1.6 repeating. I could keep doing that over and over again. Remember, we talked about how you can copy and then just change the values that you need to. I'm actually going to, for the sake of time, make a graph. I'm going to graph this function and use the table. (12x minus 3) over 2x squared plus 5x minus 3. So there's the graph. I'm going to make a table of values. So that's Control T. And we wanted negative 2, which is at 1.4, negative 1, which is at 1.67, negative 4, negative 5, that's 3.2, 2.8, and then we'll work our way to the other side, 2 and 3, that's 2.7 and 2.6. So just by looking at the graph, we have an idea of what it looks like. Negative 1 is 1.6, so that puts me about there. Negative 2 is at 1.4. So this graph goes like that. Clean that up a little bit. So there's the middle part. Negative 4 is 3.2. Negative 5 is 2.8. So this one's going to go like that. And 2 is 2.7. 3 is 2.6. Those are pretty close to the asymptote. And they look something like that. Alright, and then the very last one. So once again, we need to find the domain. So to find the domain, I'm going to start by setting the denominator equal to 0. So that leaves me with x is equal to 1. So that means my domain is x can't be 1. Okay. Which in turn leads me to know that I have a vertical asymptote at x equals 1. So that's a vertical line at positive 1. Part C says horizontal asymptote. Well, the degree of the numerator is 1 larger than the denominator, so this has no horizontal asymptote. Because it's exactly 1 larger than the denominator, it does have a slant asymptote. And we find that is with long division. So x minus 1 goes into 3x squared minus 2x plus 1. That is 3x, so 3x squared minus 3x. Subtract those. We get x plus 1. That goes in one time. I get x minus 1. I don't really care what the remainder is because that's my line. So I'm going to graph that line as my slant asymptote. So I start at positive 1 and go up 3 over 1. And we have a slant asymptote looks like that. Last thing we have to do is plot the function. We're going to have to go back to the last one and do end behavior real quick. So table values, again, I'm going to kind of cheat for the sake of time because this video is already crazy long. Clear that graph, and I'm going to type in a new one, 3x squared minus 2x plus 1 over x minus 1. I look at the table, and if we look at this, there's some weird stuff going on here. So it looks like, once again, at -1, I'm at -3, so that puts me here. At -2, I'm at -5.5. So this graph looks like it goes like that. And the other half, so on the other side of +1, remember we need to pick values on either side of the asymptotes. So 2 gives me 9, which is up here, and 3 is 11, which is just off the graph. So this side's going to go like that. Okay, so the last question then says for E, what is the end behavior? So for end behavior, I'm looking at what happens as x goes to -infinity and what happens as x goes to +infinity. Well, as x goes to -infinity, so when x gets really small, my graph is going this way. So we can say that f of x also goes to -infinity. And for the other side, it says x goes to +infinity, so we're looking this side as far as we can go. As I look at my graph is going up, so we can say that f of x goes to +infinity. And then real quick, let's go back to that last graph. Should be this one. Yep, this one here. So E, end behavior, as x goes to -infinity, what happens is x goes to +infinity. What happens? What is f of x doing? So as x goes to -infinity, that's this way. Well, my graph appears to be approaching that asymptote, which was at 5/2. And as x goes to +infinity, my graph goes this way, which also approaches that asymptote, which is also 5/2. If you have more questions, talk about that in class. Make sure you study. Remember, we're testing Friday and Saturday.